Hi, this video is a visual introduction to how item response theory scores tests and assessment. If you're watching this video, you're probably familiar with the basics of item response theory and how it is used to develop, deliver, and analyze tests and assessments. And you're probably familiar with some of the basics, such as how it estimates item parameters that can be used to describe how the items perform. This video will focus specifically on how those item parameters are used to obtain scores. We'll start by talking about just the dichotomous case when items are scored correct, incorrect, or right, wrong. Item response theory, of course, can work with partial credit and rating scale data. You can extend the concepts that you'll learn here into utilizing that data as well, but we're only going to talk about dichotomous here today. So you'll see on my screen here a Microsoft Excel spreadsheet that I've designed to demonstrate how item response theory scores. A free version of the spreadsheet is up for download on our website. I'll provide a link in the description. So you'll see here that I have a simple item bank of 8 items with their A, B, and C parameters, and I've set them all to be scored. And what we're going to do is give some response to these questions and explain visually how it's used to obtain scores. So if you're familiar at all with IRT, you know about the concept of an item response function, which I have here on the IRFs tab. Right now there's nothing there because I don't have any input yet. So what I'm going to do is give us input to the first question, and we'll say correct answer is A, and the student response A was A, so they get 1 point. And you'll note that the item response function has been filled out here. This is a simple Roche item. So that it's showing here the probability of the student getting this item correct. So a very low ability student at -2 or -3 has a 0% probability of getting it right. And a top student has a very high 99% probability of getting it right. And a middle student has an average 50% chance of getting it right. So this is not only used to describe the function of the item, but it's also going to be used as input in the scoring algorithm. And let me show what happens here. Suppose they get another question that's the same difficulty, the same parameters, but they get this item incorrect. Well, in that case, they're going to essentially get the 1 minus IRF, because the 1 minus IRF is the probability of getting a question incorrect or getting it wrong. Because a low ability student at -2 or -3 there's a very high probability, 99% chance of getting this item wrong. And the top students have a 0 or 1% chance of getting the item wrong. And of course, the middle students, it's a 50-50 either way, so they're going to still be at 50%. So what IRT does is it takes the item response function for every item that a student has answered, or the 1 minus IRF in the case when they get it wrong, and multiplies them. And when you multiply probabilities, you're going to get a likelihood. So that's then what we call a likelihood function. And back on this input tab, you'll see that I have graphed here a likelihood function. So if you multiply this curve plus this curve, you can see you'd expect it to peak somewhere in the middle. And that's exactly what happens. We get this blue curve and this red curve like that. So the blue curve is what we call the maximum likelihood estimate, or maximum likelihood estimation. That's why it's labeled MLE. And we call it that because we want to find the highest point on that curve, the maximum, and that is our most likely estimate of the score, or of the student's true theta. So in this case, their true theta is 0.0 because we had one item at 0 and another item at 0. They got 1 right and they got 1 wrong, so it kind of makes sense. If we turned each of these into 1, you'd get that same shaped curve, but it would be centered on +1. And if we change it to -1, you'd again get the same curve, and it would be centered at -1. So the student's theta estimate, or maximum likelihood estimate, would be -1. There are some additional aspects that go into calculating this. You note here that I have a red curve for the Bayes MAP. There are some reasons to use what we call maximum a posteriori scoring when you're using item response theory. One of them is if you have what we call a non-mixed response vector. So let me take this second item off here again and just leave it with the first item. And you'll notice that the maximum likelihood curve here goes up to positive infinity. And the maximum is not really defined. The maximum is going to be 1.0, but it's going to be way at positive infinity on the x-axis. So we can't really use it. So if we want to give a score for this student, we kind of arbitrarily multiply it by the standard normal function, or bell curve, or another curve if you were to have information about it, and a good reason to use it. And then we multiply that by the blue curve, and it gives us then the red curve. And you see the red curve has a maximum, which we can then use to estimate the theta. This is especially important in adaptive testing because after you give the first question in an adaptive test, you need to score the student so you can select the next item in a cat. But you can't score them with maximum likelihood because every student only sees one item, so they're going to have this undefined maximum likelihood estimate. So cats will often use the Bayes MAP as a temporary score until you get that mixed response vector, which means some right, some wrong, and then you can use maximum likelihood estimation. Another thing to consider is what happens if you use the 2-parameter or 3-parameter model. So let me put in the answer here again and change these back to 0 for the difficulty. And let's see what happens if I change the discrimination from 1 to 2. You'll see that the blue curve as well as the red curve have become much more peaked. So that gives us much more confidence that the student's theta is actually around 0.0. On the other hand, if this was a really low discrimination, let's say 0.4, you'll see that it's hardly peaked at all. And if you've read about the standard error of measurement, SEM, the standard error of measurement is kind of like the standard deviation in terms of this graph, in that it's kind of the spread of the blue curve. You can see here the spread of the blue curve is very wide. The inflection points are like minus 2.37 and plus 2.37. Whereas when we had this as 2.0, the inflection points of the curve are like minus 0.5 and plus 0.5. So it was a much, much more narrow band of the standard error. You can think of it kind of like a confidence interval in this case. And the same thing happens if you have more items. So let's say if we had 2 more items here, A, B, and these are also 0 and 0, you can see it's narrowed even more. Another thing to consider is what happens if you've got the C parameter. So let's say it's the 4-option multiple choice, and the C parameters are 0.25 for each of these. You'll notice that now the tail goes way off on the left here. We still have the same maximum, clearly defined in the middle here, but you're always going to have that tail going off that doesn't go all the way down to 0. It's going to go off to some higher value because you're essentially multiplying 0.25 by 0.25 by 0.25 over 50 or 100 items, whatever it is. It's still going to be higher than 0, even though it's still going to be quite small. So that is a very brief introduction into how item response theory scoring works. You can see I do have other things here that I'm talking about, such as classification using what's called the generalized likelihood ratio or sequential probability ratio test. And I also have item information functions, or IIF, for the first items here that get into other aspects of item response theory, but I'll be discussing those in other videos. Thank you. Bye.